relevant to the situation. I can read to you first a quotation from 1975 Simulation Council meeting. Computer-based simulation is now in widespread use to analyze systems models and evaluate theoretical solutions to observed problems. Since important decisions must rely on simulation, it is essential that its validity be tested and that its advocates be able to describe the level of authentic representation which they have achieved. Unfortunately, when you ask people about how reliable is a simulation, you very, very frequently get how many people were involved, how big the computing machine was, and such things. Not about the question you asked, how relevant is the material? And I put it into the question again. Why should anyone believe the simulation is relevant to the situation you're doing? That involves two parts. Was the calculation done correctly, and was the situation modeled adequately? Because if the modeling is not good, it doesn't matter how much you compute, you won't have a relevant answer. And I suggest you never start a simulation until you've answered that question fairly well. Now sometimes, of course, you have to start before you know exactly how you're going to come out, but most of the time you should try to answer the question before you start to get any simulation, otherwise all the work will be wasted. Now let me inject a true story. Quite a few years ago there was a technical meeting in Pasadena, and afterwards we all went to a restaurant, and I sat next to a man who had given a talk on how reliable the space shots were. And he maintained something like 99.44% reliable. Well, this is a time when there had been about 9 space shots, and so I deliberately sat next to him at the restaurant and said, well, you know that 2 people were killed on a test on the ground, and that 1 space shot blew out the side and had to be emergency rescued, and with hardly 10 shots, you can not claim that you got 99.44% reliability. And we got to argue about the thing. Now, fortunately for me, the man sitting on the other side of him saw what was going on and joined me in giving him a hard time. And we picked on him and picked on him. We finally, he said, well, everyone realizes that simulation isn't reality. I said, does the man in Washington who signs off that you can do the flight know this? He would not answer. Under repeated attempts to get him to answer that question, he would not, which means he knew that the man in Washington thought the simulated reliability was the real reliability. Well, he, after a while, tried saying, well, what could I do? I'm going to do the simulation. I pointed out a great many things he could do to try to increase the confidence that the simulation was relevant to reality. Well, that was a Saturday night. My suspicion is by Monday morning he was back to his old habits of identifying the simulation reliability with the actual missile reliability. People in simulation are interested in simulation. They are not interested in reality. And therefore, they don't look at that gap between the simulation and the reality. And that, of course, is the cause of a great deal of trouble. Now, we have long had simulators. Airplane flight simulators are the best example. They've been around for a long while. They are very, very effective. They are more effective than reality. We can put a pilot in a trainer and subject him to emergencies where he might be killed and let him see what he will do. And we've made them so reliable and so realistic that they come out sweating sometimes. I say again, we could not possibly give a real pilot the experience in that length of time that we can give him in a trainer. A trainer is a marvelous device for simulating reality. There you have a good example of virtual reality. It's been around for a long while and it's a proven success. But as we get new airplanes, the programs and details must be modified. Will the next generations of people who are more interested in simulation and reality be careful to get all the new effects of the new airplane into the simulation, or will some peculiar feature be missed? In which case, we're training the pilot possibly to fail. It's not too good a situation. You see, the problem, therefore, is not that our simulation is necessary. They are. The question is, how relevant is the simulation to reality? It's a very awkward and difficult question, and often the closeness is not measured the way you might think. Now let me discuss the worst simulation I ever did, the sloppiest one. In 1955, Bell Laboratories decided to have an open house. Bell Laboratories is a very big building with traffic jams every time the place opened in the morning and closed at night. And it loomed up there big in the rural community, and so they thought that the people around there ought to be able to find out what goes on. Furthermore, wives and husbands and children of workers ought to be able to find out what goes on, so they held the open house. It's the only time they ever did it. The idea was that people would be grouped in groups of about 15 or 20 and taken around by a guide through a whole bunch of exhibits. And one of the exhibits was the differentializer that I was at that time in charge of. Well, we were doing space flights of guided missiles. I was not about to run a space flight, or even a sanitized one, because of security problems. So I said to myself, well, a tennis game has drag, aerodynamics. It's the same kind of a problem. It's the same general thing, but it's something they could understand better, because guided missiles in '55 were not common knowledge. So I set up a game of tennis. You could play at one end, and the machine played at the other end. There were two dials. You had how hard you hit the ball and what angle you hit the racket. Outside that, you were stuck to the baseline, and there was no spin on the ball. After I went through classical mechanics and got the equations of motion, drag and bounce and so on, I called in a physicist friend of mine who was a very good physicist and a very good tennis player, and we settled down on the constants, and we settled on an asphalt court for the rebound and various other things. And after we adjusted things for his satisfaction, he said, yes, that looks like a real tennis game. Behind his back, I invited another physicist who also knew tennis fairly well and asked him, is this a good simulation? He said, well, it looks good. Now, this is only for an open house. Had it been for reality, I could have hung a tennis ball by a string, taken a variable velocity fan, blown the fan across to see the angle, to get the drag of a tennis ball. I could have dropped the ball from varying heights to see whether the bounce was in fact linear. I could have done many other things, including photographing games of tennis to see if my trajectories agreed with those in a game. I did none of them. After all, it was only an open house, and why should we go to a great deal of expense? On the other hand, let's not pretend the tennis game was accurate. Well, now let me come down to the main point of the story. I had arranged it for my assistants to tell the story about the machine and demonstrate how it worked and so on to each group. And I stood in the background to see how things were going. And suddenly I noticed a very interesting effect which I call to your attention. Not one single older person got the idea of how to play the game. Almost every child did. Now this is back in '55, before there were lots of games with computers behind them. Yes, there have been pinball machines, but not much more. The moral of the story is what I commend to you very carefully. Old people are not necessarily stupid, but they don't get new ideas very well. No, sir, they do not. And that's a problem you will always face in your early part of your career. You will constantly be making presentations to older people. They don't get new ideas well. To put it dramatically, one time I was giving lectures, one of the many times I gave lectures at Naval War College at Newport. The major was taking me to dinner before and trying to explain to me about the audience and so on. I listened for a while, and I finally said to him, what you are trying to say is they are ignorant but not stupid. He paused a moment and said, exactly. And that is the situation when you're lecturing or giving demonstrations or talking to management above you. You are facing the problem that they are not stupid, but they're ignorant, or otherwise you would not be giving them. But they also have this miserable trait. They don't get radically new ideas easily. The second reason for telling you to talk is that when you rise to the top and are at the head of the organization, please remember that's your trouble. You don't really understand new ideas, and when a radical new idea is explained to you, you don't really get it frequently. It's something important to you in two ways. On the way up, remember what you're facing, and when you're at the top, remember how bad you are as seen from below. It's a very dramatic lesson I learned from that one open house simulation. Now, I have been frequently asked to give simulations on ecology in the early days. And I would always ask, what are the rules? How much water and sunshine produce how much growth? How much this and that? And have you got some observation which I can simulate to see if I can produce your observations? For example, the growth of a forest over 10 years. Well, they didn't have such information. And as I asked for the stuff, they gradually got the idea I was not the person to ask. What they should do is find someone who didn't really care so much about being accurate. An example of that is the Club of Rome, which was very famous at one time. They predicted that no matter what we did, about the year 2020, the whole world was going to collapse. Well, investigating in the matter shows that their formulas they were using were designed to produce a collapse in 2020. And secondly, they had not even been calculating accurately. So the doomsday of the Club of Rome has faded, though for a long while it had the headlines. We would have to do something else, the world would collapse. Now, I've emphasized the need for underlying laws. You must know the laws of what you're simulating, or else you're not going to get there very well. Now, let's take economics. I have lived long enough to know that almost all economic laws, I've been told, don't always work. For example, I've lived through periods when there was not only unemployment, but there was also inflation. There are some laws of economics which are mathematical tautologies. They simply are a consequence of mathematics, and it's writing the same thing in mathematically equivalent forms. Beyond that, I thought for a long while and came up with what I consider as Hamming's law of economics. It's the only one I truly believe in. The law is, what is not produced cannot be consumed. If we do not raise wheat, it cannot be eaten. If we do not do this, then we cannot use the results. That law I'm fairly confident of, but the rest I am not confident. Therefore, I don't put a great deal of faith in economic simulations, and I think you are well aware that the economists in Washington, the world's experts presumably, do not agree frequently on what's going to happen. Some people say the market's going to go up, some say it's going to go down, some say this is going to happen, some say that. The recommendations for federal policy is not unanimous. They do not have the ability to agree upon what is happening in economics. That's the thing you want to remember. Now let me tell you another story. It happened up here at Berkeley quite a few years ago, and I will make up some numbers which are essentially correct. 100 boys and 100 girls applied to graduate school in Berkeley. And about 70 boys and 30 girls were accepted. The president of the university heard this and said, who were the people who did this? What departments were guilty of this discrimination? So he looked in and he reported back, no department was guilty. How can this be? Well, it's easy. The girls were applying in the social sciences, the arts, such as drama, English literature, poetry, and so on, where the acceptance ratio was very low. More people are applying than there are openings. The men were applying in the physical sciences, engineering, and mathematics, where the acceptance ratio was very high. As a result, of course, you see why it happened. Each department did it correctly. The difficulty was the girls were applying where there was a high rejection ratio, and the boys were applying where there's a low rejection ratio. You can say that if there were discrimination in the situation, It occurred when the girls were allowed not to take mathematics, so they didn't want to take, so they could not apply. It was not the school that was making the situation of discrimination. It was the earlier system along the way which allowed people to take what they wanted when they were girls, but more or less forced the boys to take mathematics, which left them in the hard sciences where there was many more opportunities for enrollment. Now, I tell this story because you may find yourself in the result of exactly what is well known in statistics under the name of Simpson's paradox, that when you combine data, you can get a new effect that was not there before. The combination of data produces things which are artifacts of the combination of the data. It's a very serious phenomenon. It's well known in statistics in the sense that if you take enough statistics courses, you'll meet it. Now, you may say the space flight simulations we did were also combining of data. Yes, we replaced the whole body of the vehicle by a stick, as we call it, simply a straight line. But we knew the laws of mechanics, and we also knew that when it came for mid-course correction, we would sort of tie the people down, because if, having aimed the vehicle just right, ready to fire, somebody started moving this way in the cabin, due to the conservation of angular momentum, the cabin would rotate a small amount the other direction, and the correction would not be quite right. We knew the laws, and we knew when we could and when we could not get away with vast simulation of the whole thing by one straight line. In other areas, we don't know this much, and therefore we can't get away with these enormous simplifications that we do. It's a problem, which is a very serious problem. In areas where we have great experience, we can indeed do successful simulations. Where we don't, it's a question of how accurate the simulation is. Now, if in sciences where you can, by your own actions, change the results, it's rather difficult. For example, in insurance, the insurance companies are betting you will live a long while, you're betting you'll die young. But if you take annuity, it's the other way around. Well, you can affect their tables by committing suicide. It's rather drastic, but you can do it. But they also take fair precautions. You can't take out a policy generally and commit suicide 2 days later to collect on it. There are generally clauses which require you not to commit suicide within a given length of time, if ever. So they have realized that a situation where they are, where you, by your behavior, can affect their tables and their calculations, they are extremely cautious. Well, now let's go to the stock market, which I've mentioned a few times. The stock market is the result of a large number of people acting. Now, you, by your actions, can change things. If there were a widely known method of making money in the stock market, it would have to fail, because then everybody could use it and everybody could make money, and to a great extent the stock market is a zero-sum game. What somebody wins, somebody loses. After all, you sell some stock, somebody else buys it. If you buy some stock, somebody else has sold it. Yes, there's a general trend up, but on the average it's locally a zero-sum game. Therefore, I say again, you cannot have a theory which will enable you to predict reliably the stock market and have it widely known. I also warn you the thing, as I told you before, is somewhat rigged and crooked, and if you act on inside information which is illegal, you can go to jail. That the people who are in the business act on inside information is perfectly obvious. And they know how to act so it can't be proved in court, so you are safe. But you as an outsider, you're going to break the law if you act on inside information. Plus the fact that a fair amount of so-called inside information is deliberately floated so you'll think it is, act that way, and they can make money on your actions. So anyway around, the simulation of the stock market is going to be very difficult, and if you do it, you're going to have to keep the results very, very private if you expect to make money. Now, I say very simply, beware of any simulation which the humans, by knowing the outcome, can change it by their behavior. Now, we have coped with this problem in other ways. We have a method called the method of, the method of scenarios. It's what Spock did in the baby book. He looked at how babies behaved in the early years. And he said, not how your baby would behave, but rather, on the average, when do they begin to walk, when they begin to talk, when they begin to say no, and such other things. He did not predict the individual one, he predicted average traits. He gave scenarios of what you could reasonably expect. He also limited himself to a great extent to those phenomena which were biological rather than cultural. Because cultures can change rapidly, but biology cannot. The biology of children born now is not terribly different from that born quite a few years before. But the culture is very different. So he restricted himself a great deal to scenarios. And this is in fact what I am doing in this course. I cannot tell you what the future will be. I'm trying to give you a large number of scenarios of what kind of things are likely to happen. It's the best that can be done in these situations where people by their behaviors will affect things. If you predict a certain phenomena, and humans know it's going to happen, they will promptly do something else. So you can't do much more than that. Now, there's a great many things you can do about checking up on accuracy. Is your simulation relevant, or have you neglected things? First, does the background field support the assumed laws to a high degree, as they do in classical mechanics, or relativity, or quantum mechanics? How sure are you that some small but vital effect is not missing? For that, you need an expert. People who think they can come into a field and simulate without expert guidance are apt to miss very basic effects as well known, but they didn't stop to think. And so not being in there, the simulation will be not accurate. Also, do you have the initial data? Can you get data accurately enough to do things? Most data is very much less accurate than it's thought to be. It just does not work out very well. And if your data going into the simulation is not accurate, it's likely to be that the simulation itself is inaccurate, but we'll take that up in the next lecture. Do you have any cross-checks? As I said about the simulation, I would like to compare a real tennis game with the simulation I did. Otherwise, how do I know the thing is going to be accurate and relevant? There are a lot of things you can do of those kinds, but ultimately you're going to have to take some risk in the business. Can you check on conservation of energy and conservation of mass and so on? I have never to this point mentioned another trivial point. Are the equations on paper actually translated correctly into a program? Are there program goofs? You all know that frequently programs in use for years still have serious bugs in them. Well, in a simulation, particularly when you're using it as a basis of action, a bug can cause a great deal of harm. In fact, in some simulations, such as wargaming and business training, you can cause enormous trouble by training the person to play the wrong game. Or if you want to play the right game the wrong way. You have to get those simulations very accurate indeed. Now let me tell you another story about this problem of getting the problem into the machine correctly. Oh, by the way, I should back up. The story I told you about Berkeley and the students' enrollment, the trouble there was obvious. The president of the company the president of the university supposed that the students were applying uniformly over the whole of the school, and therefore seeing a 70-30 ratio was not good. He failed to realize that people were not applying uniformly. The women were applying in one area, the men were applying in another area, and they had different acceptance ratios. The assumption there was a tacit one, but it's likely to be made by a simulator every time. He just made the assumption in his mind without thinking that, of course, he did not know there was a bias. Well, let's go on. Here's a story that is interesting and what you can do about these matters. The government came to Bell Labs and asked them to apply for a study of what happens in the upper atmosphere when an atomic bomb goes off. How long before, or how long afterwards can you go without seeing? How soon will the radar be able to look through the explosion to see something? Therefore, you have a problem of what happens to the upper atmosphere, ionization, and so on. Now, it turns out that there are an enormous number of different possible interactions between the atoms. There's something like 100, give or take a few. And there's not agreement upon which ones should be put in. So I suggested the following, that what they do is write a single card for each interaction along with all the constants involved in that interaction, all the capture cross-section and so on. Then they would select the cards they wanted to try for that experiment, that computation. And I would have them then write a program which would write the program of the 100 differential equations, because I did not think that they could get 100 differential equations into the machine and get them all accurate. After all, a coefficient occurs up here with one sign, it occurs down here with the opposite sign. If those two don't occur exactly right, the simulation isn't going to be correct, because those going into the state, out of one state, and going into another state must balance. You can't lose particles. Well, they saw the wisdom of that. And so we wrote the program which, from the raw data, would create the particular set of differential equations and write the program for it so that they could concentrate on the chemistry. That's the thing I tried to do. They were chemists. Their problem was what chemistry was going on. They were using a machine. Yes, I had to explain to them how the machine did and did not compute and some other things. But fundamentally, I wanted to keep their minds on where they were living experts. That's the most important part of a simulation, to get the experts doing the job and not get commercially available simulators who don't really know the problem. Well, it worked out fairly well as far as I could find out. In summary, the reliability of simulation, of which you will see many in your careers since it's becoming increasingly common and necessary, is of vital importance. It is not something you take for granted just because a big machine is given it. You are responsible for the decisions you make, no matter what bad day they give you. With the power of decision rests the responsibility. Therefore, you have to ask yourself, when you get simulations, of which you're going to get many, is this relevant or is it not? If it isn't relevant, I'd better ignore it. If it is relevant, I'd better pay close attention to it. Because simulations can simulate much more complicated situations than you can think your way through. And it's a problem which we'll face many times with many, many problems. Do you believe the simulation is relevant to the situation? Can I track down these things or can I not? Now, you can't go through all the details. You have to depend to some extent, but you can ask for cross-checks. You can say, what happened in this situation? You may know some situations, and you can ask them, what did you find in this? And have them run those cases to convince you that they have or have not got a decent simulation. It's a very vexing problem. I have no simple answer to the question, no silver bullet, no magic drink you can take or anything else to decide that a simulation is or is not relevant. Now let me return to a problem which I've been disposed of for some time, the relation of analog and digital computers. If you want now, neural nets. The claim was made in the early days that because the simulation in the analog computer was continuous and the other was sampled, that the analog one might have more accuracy. Well, there's a theorem. If I have the information from minus infinity to plus infinity, then you remember Nyquist says 2 samples for the highest frequency present, and I can reconstruct the signal from the samples. Well, if you have a shorter run at such things as I told you in digital filters, by theory and by computation, I came up with something between 7 and 10 samples for the highest frequency present was needed for the typical integration formulas you use on integrating differential equations. Therefore, since I believe all equipment is essentially band limited, because if it were not band limited, it would have infinite energy. And I don't believe in infinite energy, so I don't think signals are other than band limited. They sooner or later fall off. So there's a place out there where you can successfully sample at a given rate, and it can capture essentially all the phenomena. Now, I've gone through an argument many times because the analog people said, oh, they can calculate things digital can't, or vice versa. And I also told you the story of how, from getting the engineers what the highest frequency was that I had to worry about, I could figure out the sampling rate for a big computation. They are connected. On neural nets, it's the same thing. There is a bandwidth in this stuff. They aren't infinitely wide, and therefore if you're doing an analog neural net or whether you're doing a digital neural net, doesn't make that much difference if you are sampling at a high enough rate. They are equivalent one to the other, pretty much. Now there's a difference, however. In my day, analog computers had components 1 part in 2,000. You may well now be able to get 1 part in 5,000, but it's going to be expensive. You cannot get 1 part a million very often. That's only 6 decimal places. Well, digital computers compute to 10 or more frequently. So digital machines can calculate more accurately. And if a computation is what we call deep, goes down, numbers are used to numbers all the way down instead of more or less a great many at the upper level, then an analog computer likewise cannot cope because it will lose accuracy as it goes on and on and on and on. So digital machines and analog are not the same. The digital machine has the advantage that I do not go broke trying to be very, very accurate. And in very accurate situations, I simply have to turn to a digital machine. Otherwise, there isn't that much difference between them. The analog machine is very easy to understand. It runs very well, and it runs in parallel, and it has advantage. On the other hand, it's intellectually dull. The scaling to put problems on analog machines is rather hard, particularly time scaling, so that we find now very little analog computation. But I think it's a mistake. I think you'll find in time analog computation is very good. And particularly neural nets are a very interesting example. They seem to be a way of connecting up a bunch of parts under limited restrictions so that the, shall we say, least squares optimization will cause the network to come down to a given state. You decide how many stages you want, what feedback paths you think are important, and either the analog or the digital one, given now a large amount of data, can find patterns, can do other things that would be very hard for a human to write or program or think their way through. The difficulty is, in my mind, will I dare to act on a result from an analog neural net which I do not understand really why it is so? Would I dare to operate in medicine if I don't understand why the neural net said you had this or that thing and therefore this or that operation should be done? I am very wary, although I'm not unwilling to go down the path of not always understanding. In the past, science has been based upon heavily understanding of what we meant. Now, I don't know what the word understanding means. I don't know what the insight, meaning, or any of those things mean. Nevertheless, most of you have an idea what I mean when I say we understood what we were doing. Neural nets give answers without necessary understanding. Now, they've been used successfully, most dramatically, on the Tokyo subway. They give a smoother ride, they stop more accurately, and they use less power than do human operators of the subways. So neural net combinations can frequently do remarkable things in control situations, and they can also do remarkable things in finding patterns that you can't find. So the analog computer is not to be neglected or ignored. Now I want to come down to some general talk about this matter of you and simulation. As the world gets more complicated, the human mind does not work well with lots of details, and frequently you cannot see your way through. Thus the atomic bomb, they had an idea how it would work, but just how the shells would come down and collapse under a shock wave, what the shock wave would actually do, how long the shell would be held together before it blew apart, these were questions which were vital if the atomic bomb was to work. In the same way in weather. You'd like to know what is going to happen tomorrow. That depends on what is happening today. What albedo does this block of air have? So consequently, how much sunlight will absorb, how much will heat up, and so on. The difference I told you at last lecture. One was fairly stable. Small deviations made very little difference. The other was not stable, and small deviations produced large differences. So it makes the weather prediction much, much harder than it does others. So simulations you can do depend heavily upon this topic, which I'll talk more about next time, of how much feedback there is to control the stability or the instability. Now, you can't get along without simulations. You're going to have to do a lot of them. And as you move from the hard engineering, which I've chiefly done, to the softer ones, it's not that you don't want to do a simulation. You have to ask the question, is it relevant? Have they captured the behavior, particularly in human behavior? We're going to want more and more to answer questions like, if we reorganize along this way instead of that way, how will the system work? Because we're going to have a great deal of reorganization. Organizational structures have been under pressure for some time to change. And you'd like to know, well, if I put this in, what happens? Now, in many experiments in life, you cannot go back and really relive the other. For example, suppose in your life sometime was a choice of marrying one of two people. You may later years wonder, what would have happened if I married the other person? You can never know. In the same way, if you organize a corporation in a different way, you cannot go back and find out what would have been if I had not reorganized. And if you try going back to the first organization, you are not going back without this memory of the first reorganization, which upset so many people. It's impossible to do many things that you would like to do on experimentation before you actually take the step. That means you have a simulation. And since more and more we are recognizing the role of humans, more and more our society is human-oriented rather than thing-oriented. Yes, people want things, but the number of people working in manufacturing is relatively down as against the people in the more manufacturing and the more management side. And so it's going to be management situations which many of you are going to face. And there will be this very elusive thing. Now, I think may have told you last time, maybe I didn't, I have a rule that I use when I'm in these bad positions. I like to have an expert around who has an intuition of what will happen. Somebody who's been through those kind of things. Now, if I make a simulation, and I get one answer, and the expert gets another, and the experts who know the business say, well, it's not the way it's going to happen, what do I do? In a situation where the technology is changing slowly, I bet on the simulation. I'm sorry, I bet on the expert, because his experience is much the same. Where the technology is changing rapidly, I figure his intuition of past experience is irrelevant, and therefore I can ignore it. I'd best ignore it. That comes down to something that humans have called a gut feeling, intuition, or whatever you want to call it. It is a remarkable device that humans have, their intuition. It summarizes, in some sense, an enormous amount of experience. You don't know how it works, but something tells you it isn't going to work out that way, or it is going to work that way. You don't reason it, you feel it. And this instrument that you have in you for intuition is very, very powerful when the situation is relevant, when your past experiences fit. When your past experiences do not fit the situation, then your gut feelings are not so good and you better ignore them. Well, next time I'll finish up with simulation. We'll go on then on to a bunch of miscellaneous topics. Normally these lectures are on whatever topics the students have wanted, but over the years I've settled down on a few of them. But if there are any particular topic you want me to discuss, let me know and I'll see if we cannot get a lecture on that topic for you. So meanwhile, I'll see you next lecture.